In this second part of chapter on dienes, we are going to examine very important reaction of dienes, and that's the Diels-Alder reaction. Diels-Alder reaction is a reaction between a diene and a dienophile. A diene must be a conjugated diene, as shown here, on example of 1,3-butadiene. Dienophile is an alkene, but not just any alkene. It has to be substituted alkene, and the substituent must be an electron withdrawing group. So dienophile is an alkene on which we have electron withdrawing group directly bonded to the double bond. Reaction between a diene and dienophile proceeds to give a 6-membered ring. This is cyclic concerted reaction. We actually call these reactions pericyclic reactions. Concerted reaction means that there is no intermediate, or there are no intermediates in a reaction like this. This is a single-step reaction, which means that we have starting materials, transition state, and product. In the lower part of the slide, you can see the reaction mechanism. We can, of course, push arrows to show bond breaking and bond making, and in the middle you can see the transition state. So 6 bonds are involved, and we have cyclic transition state in which bonds in a ring, in a 6-membered ring, are all being either made or broken. In the course of reaction, 2 pi bonds are converted into 2 sigma bonds. So we start with 3 double bonds and we end up with only 1 double bond. This is method for formation of 6-membered rings, and cyclohexene is a reaction product. Here is another example of Diels-Alder reaction. Nitrile group, CN group, is a good electron withdrawing group, and you can always figure out what is the reaction product by pushing arrows either clockwise or counterclockwise. That doesn't really matter whether you push arrows clockwise or counterclockwise, the outcome is the same. If there is no dienophile available for reaction, then diene may react with itself, because actually a double bond is electron withdrawing group. So one double bond may activate another in a diene to act as electron withdrawing group, so that one of the double bonds is a dienophile and reacts with another molecule of diene. So here on example of 1,3-butadiene, you can see that 2 molecules react. So this is so-called dimerization reaction, and product is 4-vinyl cyclohexene. If diene and dienophile contain substituents, then there is possibility for formation of different regioisomers. In the first example, here we can see reaction of 2-methyl-1,3-butadiene with itself with another molecule of 2-methyl-1,3-butadiene to give the product. This product is known by its trivial name as limonene. We get only single isomer. If either of the diene or dienophile molecules were turned upside down, we would get a different regioisomer. This is the only regioisomer that is obtained. Note that 2 substituents on cyclohexene ring are in positions 1 and 4. Alternatively, in the second reaction, we have reaction of 1-chloro-1,3-butadiene with acrylic ester. Acrylic ester is something that we did not cover so far, so you don't need to know the name, how to name such a compound. In any case, product has 2 substituents in 1,2 positions. So as a result of this Alder reaction, 2 substituents are going to end up being in either 1,2 positions, that means next to each other, or 1,4 positions. They will never end up being 1,3 relative to each other. Note that in case of the second reaction, numbering is actually not 1,2. Numbering would be 3,4, but the 2 substituents are related to each other as 1,2 substituents. They are on the neighboring carbons. We call this regioselectivity ortho-paraselectivity after substitution patterns of benzene ring. Benzene is aromatic compound, and there are 3 possible substitution patterns on benzene ring. If 2 substituents are next to each other, occupy positions 1 and 2, that's orthoisomer. If they are in positions 1 and 3, then this is called meta-isomer, and if they are in positions 1 and 4, that's para-isomer. So if we were to imagine that this is benzene ring, that cyclohexane ring is benzene ring, of course it isn't, but if we assume that it were, then substitution pattern that results from a Diels-Alder reaction is ortho-para, and we never get a meta product. So that's a convenient way to memorize regioselectivity of Diels-Alder reaction. It is always ortho-para. Alternatively, more accurately, it is always 1,2 or 1,4 and never 1,3. If dienophile contains two substituents, then we may have cis or trans alkene, and this stereochemistry is preserved in the product. In a cis alkene, we have two substituents on the same side of double bond, and in trans they are on the opposite sides of double bond. That is preserved in the product, so cis alkene reacts with a dienophile to give cyclohexene ring. And in the ring, two substituents are on the same side of the ring, so we end up with cis substitute ring, so cis product. And in case of trans dienophile, reaction with diene, 1,3-butadiene, gives cyclohexene with two trans substituents. So stereochemistry of the original dienophile is preserved in the product. The only difference is that we go from double bond to the ring. This is excellent reaction for formation of very complex molecules, particularly molecules that contain several fused rings. Here is an example of 1,3-cyclopentadiene reacting with acrylaldehyde. Product contains two fused 5-membered rings, and that product has particular selectivity. It is endo product. Note that carbonyl group C double bond OH, that's an aldehyde group, or C double bond O is carbonyl group, is below the plane of the ring. This is so-called endo product. Alternatively, it could be in a position occupied by hydrogen, and that would have been exo product. Exo and endo are terms used to describe different stereoisomers on fused rings. In case of fused rings, we can identify a couple of bridges. They are parts of the ring that do not contain substituent. So those bridges, if they are different, will be longer bridge, one that contains more atoms, and shorter bridge, one that contains fewer atoms. If substituent, shown here as X, is closer to the shorter bridge, that's exo product. If substituent is closer to longer bridge, then that product is named as endo. DielsAlder reaction always gives endo product. Here is an example of reaction of two cyclic compounds. Cyclic diene, 1,3-cyclohexadiene, and cyclic dienophile. This compound is called maleic anhydride. Resulting product has three fused rings, and it is endo product. In this case, two substituents are closer to the double bond, to bridge that has double bond. Finally, DielsAlder reaction also works on triple bonds, alkynes as dienophiles, as long as alkynes contain electron withdrawing group or electron withdrawing groups. In such case, only one of the two pi bonds of alkyne reacts. The other one remains intact. So product is 1,4-cyclohexadiene with appropriate substituents. This completes our study of DielsAlder reaction and our study of dienes. Next, we are going to look at aromatic compounds, their properties and reactions.